Hello. In this presentation, we'll be going over TidesDB. The presentation is titled Riding the Tides, Building a Modern Storage Engine. This presentation is for MariaDB Foundation. So who am I? Well, I'm Alex. I'm the creator of TidesDB and lead maintainer. My background really is just really obsessed about storage. I've been programming since I was young. Very curious, so anything that really I got into, I had to take apart and understand. And over time, just really building different storage systems, whether it was document-oriented, relational, key value, uh, distributed, let's say, as well. Just picking apart these different designs and figuring out what the bottlenecks were and how to approach these implementations from first principles. And yeah. Just very, very crazy obsessed about databases and just love building them and love the problems that they bring up. So what is TidesDB? So TidesDB is essentially like a key value storage engine, similar to RocksDB, BerkeleyDB, let's say. Um, TidesDB is architected on LSM trees. LSM trees, log structure merge trees. There's a lot of features that TidesDB offers, such as ACID transactions, time to live, TTL, which is built into the engine, save points, commit hooks, and a lot of cool different features as well, which are pretty much essential for building such a tool as a storage engine, right? You have something like a game engine, which gives you all the tools for building games. The storage engine is like a same idea, which gives you all the tools for building databases. Um, what's really cool about TidesDB is that it's adaptive and self-tuning. So a storage engine like RocksDB does a lot of fixed configurations, and that's you know, levels and capacities at levels, etc. But TidesDB is adaptive in that regard, and we'll get into that. Um, and let's see what else we can mention here. But TidesDB is a C library, right? But it can be accessed through a variety of different FFI libraries in which are accessible. So essentially, if you create a database in one library, the C library, you can open those database files through any other library and even other systems, right? All the database files are completely portable, and the system is multi-platform, right? So working on all different architectures and platforms. Yeah, we can. Actually, I'll mention one more piece here. When you have a process running TidesDB, you can have many TidesDB instances in one process, so long as they're configured uniquely, right? So, yeah. So there's usually a trade-off with LSM trees, right? So let's say you have InnoDB or BerkeleyDB, which are more B plus tree based. Uh, which is okay, right, for reads, but writes definitely suffer with that. With an LSM tree, writes are batched in memory, and then periodically they're flushed to disk as sorted runs, right? So there'll be a bunch of sequentially written files, log files, which tie directly to a mem table, and periodically there will be sorted runs which traverse beta memory skip list and create these SS table files, right? The issue with the LSM tree in many cases is obviously write amplification, where 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 a key can get written, let's say, multiple times, or where a key can live in multiple files, right? And this indirectly causes read amplification as well. Um, but with an LSM tree, you have your hierarchy, which is L0, which is your unsorted files, and then L1 plus is your LN plus is your disk levels, right? And the capacities grow, so but they adjust in TidesDB. But let's say the mem table is 64 megabytes. Each level will grow exponentially 10x. In TidesDB, we have this idea of column families, which we'll get into in a moment. But each column family has its own essentially LSM tree, right? So it has its own memory buffers, mem table, and disk levels, right? So each column family. Um, and yeah, we can. Well, let me explain one more piece here. So these sorted runs, they're when the mem table reaches a configured threshold, which by default is 64 megabytes, as just described. At that point, it'll become immutable and queued for that sorted run, so a flush. The flush workers are what dequeue work and do that work. So it'll create files for we'll create sorted files for the column family. And yeah, you can see the transactions there. We'll get into that as well. So let's just move to the next slide here. So the column families, which I mentioned earlier, they're independent namespaces. So like as stated, each column family can have its own LSM trees. Each column family is separately configurable, right? So you can configure different compression algorithms and buffer sizes and level size ratio and a lot of different things. Bloom filters, block indexes, stuff like this. You can see in this in this diagram here that the mem table is comprised of the write-ahead log and the skip list. So when writes come into the database into a specific column family, they're written and appended to the write-ahead log first, and then into the in-memory skip list, right? Okay. And you can see the disk levels. So earlier we mentioned the background workers that are tied, or you could see in the diagram earlier that each database instance has a compaction worker, different worker threads, and these worker threads, they do different things. So obviously the flush worker dequeues work for all the column families, and it does those sorted runs to disk. The compaction worker takes compaction work, so merging different SS table files for different column families. DQs work, and these workers, so the compaction and flush worker, there can be many of those. So by default, it's 2 of each, but you can configure that at the database level. The sync worker is like TidesDB, you can have different sync modes, so sync none, sync interval, and sync full. So the sync worker, if you have sync interval, the sync worker essentially f-syncs the write-ahead logs for all the active write-ahead logs for all column families every n amount of milliseconds. And yeah, so the sync though, like when a flush occurs and there's a sorted run or there's like a new file being created internally, those are durable. Like f-sync is used for internal work, but hot path work, like writing to the write-ahead log, if you're in sync interval, there's a worker that takes care of that for all column families. The Reaper thread, it essentially acts as like a Reaper, right? So it deals with file handle eviction. So if there's a lot of SS table files globally for the database instance, by default it's 512 file descriptors. If the system reaches up to 500 active file descriptors open at that time, the Reaper evicts the least access, the last accessed and oldest 25% of the file descriptors. So this just prevents exceeding system limits for like OS system limits for file descriptors. But the Reaper thread also takes care of um, retired like array reclamation. So because the system is primarily lockless, right? So what that means is we use a lot of ref counts on the different sources and structures and objects that might be existing during the runtime, like during when the system's running. So the Reaper thread takes care of having to essentially reclaim or free specific sources. Like let's say an SS table array changed, it'll reclaim like the old array, right? So once the array is not like an old array is not used, let's say there's a new or old, like a new SS tables added or old SS tables added to a specific array, or it really what the SS table does is it just reclaims uh, um, reclaims memory and space, right? That's what it does there as well. The Reaper also deals with like memory pressure, so every like n milliseconds, the Reaper essentially sums like all the current memory usage in an efficient way where it doesn't block anything. It does it like pretty much all atomically in the background, and it checks because this you can set the database to use a max memory limit, and the Reaper essentially checks, right? So it's like, okay, are we reaching like max memory? Let's purge what's in memory right now, or let's force a compaction, and so the Reaper does a few different things. It's pretty interesting. So I mentioned before that each column family can have its own mem table, but there's a mode in TidesDB where at the database level you can configure for a unified mem table. So at the database level you'll have one mem table and one skip list and write ahead log, but they're shared between multiple column families as opposed to multiple column families using multiple log files, right? So so instead of n separate wall files, it essentially cuts I/O, right? Linearly. Now you might think like, okay, like how does like sorted runs work and all these kind of things? Well, when the flush worker has to like flush a unified mem table, it just groups like consecutive keys by like their column. Like there's a unique column family prefix, and then it writes those SS table files per column family. Everything else is pretty much the same, but yeah. So this is like very good in MariaDB's case, where like the MariaDB plugins case, where like a table can have many secondary indexes and primary index, which we'll get into, but each there's a lot of column families, right? So the unified mem table makes this highly efficient. So we're going to discuss a fundamental key component in TidesDB, which is the block manager, which is like an IO abstraction layer, and most files in TidesDB go through this the block manager. The only file that really doesn't is the manifest file, but like an SS table, it's made out of a klog and a vlog for key value separation, which we'll get into. But yeah, so the block manager is self-describing. So what that means is each block, it describes how much data is inside the block. You can see here when you have the block, when a file is managed by the block manager, there's a block manager header with a magic and a version in the header, which identifies the file as a block managed file in TidesDB. And each block in the block manager has a block header and the block footer. In the block header, you have the size of the data in the block, the checksum of the block, and the data. And the footer in the block is made out of unique magic number in the footer and the size of that data in the block as well. And essentially what this allows for is self-describing, right? So each block can be different size, and with that footer in the block, we can seek to the end of the file, let's say, and read the block footer and know how much data to read inside of that block. And this also allows for fast backwards iteration in the file, right? Reading blocks forward and backwards. So obviously the block manager has cursor support, right? So sequential and random access, forward and backwards, partial reads. And yeah, we use this very much. So like in TidesDB, we have a validation modes. So we have a strict mode and a permissive mode. So the strict mode is like we reject all corruption in a block managed file. So what this means is we'll like traverse to the end of the file, or like iterate. We'll seek to the end of the file and then check if that last block is valid. If it's not, then we know that the block managed file is essentially corrupted, right? Because it's an append only block manager, but it runs in parallel, so blocks can be written in parallel. No locks. But the last block, let's say that the last block was, let's say there was a power outage and the last block wasn't effectively written properly. We know that let's say the compaction or the flush wasn't fully completed. Then we know in strict mode we can delete that SS table. Now in permissive mode, let's say in recovery for TidesDB, we essentially validate the last block of the log file, and we check if it's okay to keep appending to that block managed write ahead log file, right? If that last block is not valid, we'll truncate it to the last valid block. And yeah, so log free, append only, and it uses atomic reference counting and check. I'm sorry, at the block manager level, there's like an atomic offset, right? And every thread, let's say there's multiple threads writing to this block managed file. The atomic offset is what determines what's reserved for each thread, right? So that's how the parallel writes working utilizing pwrite for POSIX, right? But we have a compat abstraction where we run on all platforms, utilizing what platform specific APIs there are for the platforms. Yeah. So the SS table files, they consist of two files. I mean, the SS tables, they consist of two files: the keylog and the value log. So if a key's value exceeds over 512 bytes, it's the value is put into a value log, right? When a flush or compaction occurs. The K-log is made up of 64 kilobyte blocks. And these blocks, and each 64 kilobyte block has a min and max key prefix of the keys that exist inside of that 64 kilobyte block. Okay, so the key log also has 3 auxiliary blocks at the end, which are like the block indexes if enabled, and the serialized Bloom filter, serialized block indexes, and like serialized SS table meta details. So in the key log, and yeah, the value log is like a different size blocks and only values in which the value is over 512 bytes, and obviously on reads we'll retrieve that value from the value log if it exceeds over 512 bytes. This allows for the key logs to be rather compact, and having the fence min and max in each 64 kilobyte blocks. This enables us the min and max are block indexes, right? That's a block index. The sparse sampling, right? So you know, when you create a column family, you can set you know, how you want your block indexes to be sampled. By default, each block is sampled, like each min max key prefix is sampled, and you can even set the length of the prefixes you want to sample. But you know, we use this for searching, right? Like a binary search, like which block contains this this key, right? Within a keylog. It's like an index for the keylog. Okay. So in TidesDB, you can have a optional B+ tree layout. So as I said, the keylog is a like an index for like it's obviously like each block has the keys and the values, right? But the min and max is like the index, right? So we're able to determine, does this block have this key specifically in the keylog? But let's say you're in a memory constraint environment. You can use like a B plus tree. So the keylog itself becomes the index, right? So each node is 64 kilobytes. Um, the B plus tree keylog obviously excels at point lookups. And yeah, it's tree traversals versus scanning blocks, right? So it's going to be rather fast. Um, and yeah, you can set this per column family, so works pretty good. Um, so how do we achieve like this modern performance? Building this modern kind of system is obviously well, not obviously, but in our case, we're utilizing a lot of lock-free data structures. Most of the system is lock-free. The block manager, the skip list are two primary components, and which are lock-free. The clock cache as well. Um, but the skip list in TidesDB is completely lock-free, so optimistic concurrency. We use compare and swap. Each key maintains a version chain, so the newest key being first. Our skip list in TidesDB implements a arena allocation with an arena bump allocator, so contiguous memory allocation and very fast bulk deallocation, like on flush, for example. The skip list implements bidirectional traversal. So we have forward and backwards pointers at each level. Another piece with the background Reaper in TidesDB, it caches the syscall time, right? So we have an atomic cache time pointer, like a cached time, yeah, pretty much the current time which is cached, which the Reaper populates. This is passed to the skip list as well. So like during time to live checks, when we have to check if a key expired and is going to be marked deleted, or with a tombstone, like a deleted key, like a delete is essentially a new version, a flag in the skip list. But yeah, we pass this cache time pointer to the skip list, and it allows for efficient TTL checks. And yeah, so this enables MVCC, right? So yeah, the skip list itself is a rather optimistic data structure. So it's essentially like a sorted linked list. Let's say that, and it's more efficient than, say, using like an AVL tree. It's much easier to implement a skip list and make it lock free than in a balance tree, let's say, because rotations really touch multiple nodes, which is very hard to do without locks. So now let's go through and discuss the write path in TidesDB. Just take a sip of that. So the write path in TidesDB, let's say you want to begin a transaction. You essentially begin a transaction through the database. You'll get a sequence number, and a transaction can run through multiple column families. Let's say you commit the transaction. At this point, my apologies. At this point, so yeah, let's see here. So you essentially begin the transaction. You get a sequence number. You run through your operations, which can run through multiple column families, right? Which can be all or nothing, which is all or nothing. On commit, and then essentially on commit, we're writing to the mem table, which is the write ahead log in the skip list. And then if the threshold of the mem table is reached, like the write buffer size is reached, At that point, there's a swap done, a CPU instruction done, swapping the mem table for a new one, and enqueuing the mem table for a flush, right? And then we go to that flush, how the sorted run works, but very simple write path. And we'll get into more about how this all works here. So the sorted run to disk, the flush, as I mentioned, when the mem table exceeds its configured write buffer threshold, which by default is 64 megabytes, it's enqueued for flush, and the threshold it adjusts on the so if the system is going through a lot of load at the time, it's gonna just respect its 100% threshold, which is 64 megabytes. But if the system is not used that much and there's it's pretty quiet, then it's gonna allow for a little bit more data to be written to the skip list and then flushed, right? So you can get 100% of 64 megabytes or 150% of 64 megabytes, just to allow for the mem tables to fill up a little bit more. Okay, and you'll see how the queues work. The L0 queue, which is the queue of immutables. All right, so that it's sometimes a little bit better for the queue to fill up with larger mem tables. When the system can do that. So we have this idea in TidesDB of like a write back pressure and flow control. So in TidesDB, you can have the L0 queue threshold is like 20 mem tables. So essentially, in this example, I think it's different in this example. This is what, 8? No, it's more than 8 here, but essentially, the way this works is the system observes the L0 queue and it determines how large the queue is. So let's say there's 4 mem tables in there. It's not going to apply any delay to writes, right? But now let's say there's a fifth a fifth mem table that comes in there. At that point, each write, it's going to apply a bit of breaks to the write, to each write. So flushes, so the L0 queue can catch up, right? So the flushes, the sorted runs can catch up, and as more, like let's say that writes are coming in faster than the system can handle, it can get up to the point where the system it's gonna apply more and more breaks until the point of blocking writes, until the queue drains a little bit, right? So just to prevent ohm out of memory. And then there's also that global memory pressure. So the Reaper as well checks in the Reaper as well does a check in the background, and is also, as stated before, checking like the current memory and checking if it has to do any proactive action on the memory structures, to force a flush or force a compaction, etc. Right, to purge things in memory. So let's say the memory usage is getting rather high. The Reaper can also take action to prevent out of memory usage. So yeah. So in TidesDB we have 5 isolation levels, from read uncommitted to serializable. With serializable, we implement serializable snapshot isolation with a simplified so it's a simplified SSI implementation. So the SSI works in a way where we're tracking read and write, write and write conflicts. It's a rather simplified SSI implementation, so we don't implement like a full precedence graph at the library level. So false aborts are possible, but rather rare. And yeah, pretty basic in this regard. So now the read path is where things start to get rather exciting. So in in the read path, when you want to do like a, let's say, a point lookup, you're going to begin a transaction and start your, let's say, do a get for a certain key. And at this point, it's going to go through multiple sources through the column family. So it's going to go through the active mem table, and if it doesn't find the key in the active mem table, it's going to check the recently enqueued for flush mem tables. And then if it doesn't find it in there, it's going to obviously check the disk levels, right? So L0 and then up to L1. So L1 is the sorted SS tables. So at this point, it's going to look at the SS table. It's going to start at L1 and look at the SS table meta details, right? So each SS table has like a min and max fence keys, which will tell us, should we even go to the Bloom filter and check the Bloom filter if enabled for this key. So if we determine we should check the Bloom filter, we're going to check the Bloom filter. And if the Bloom filter tells us, hey, this key is could be in here, at that point we're going to utilize the block indexes in TidesDB if enabled. And at that point we're going to get the specific block offset in which that key lives, right? But what we're going to do before reading disk is check the block clock cache, right, which is a lockless data structure, like a cache which implements like clock eviction algorithm. It's a partition clock cache, lock free, and yeah, it reads disk blocks and B+ tree nodes and caches them. It's split across multiple partitions, so like 4 CPU core, 4 per CPU core, to reduce, let's say, thread contention. And yeah, like the clock cache algorithm and the clock algorithm. So each entry has a recently used bit, and the clock hand sweeps around, and if the bit is set, it clears it and moves on, and then a second chance, right? If clear, the entry gets evicted. And lookups are fully lock free with 0 copy reads for the block cache. But we're going to check this block cache or the B+ tree cache and see if we can avoid the disk read, right? But if we have to do the disk read, we're going to do the disk read for the block and then send that to the block cache, right? So we discussed about how in the LSM tree we have multiple files, right, that can live through multiple levels. And now we have to obviously deal with this utilizing compaction. And the goal with compaction is essentially to reduce read amplification. So we're going to merge those different SS table files, essentially discarding older versions, discarding Tombstone and expired keys, right, through time to live. And in TidesDB we have 2 triggers. So let's say L1 when it hits n SS table, which was a 4 by default, or when any level exceeds its capacity at the time. And these are 2 triggers in TidesDB. Now we have this idea in TidesDB of a dividing level, right? The dividing level is a computed target near the bottom of the tree, and this is all configurable at the column family level. And this is where most merges really aim to be. Now we implement this academic paper called Spooky, and essentially what we have in TidesDB is we have these 3 merge modes, which are auto-selected at the time of when the trigger is when the trigger is essentially hit, right? There's 3 different merge modes which we have in TidesDB, which is the dividing merge, which sweeps level 1 through the dividing level down into the next level, partitioning output by the key range. We have preemptive merge, which is a smaller merge between two adjacent levels when one level fills up earlier than expected. And then we have partition merge, which is essentially like a cleanup pass that runs if the dividing level is still full after the main merge. These merge operations are done through like a min heap that pops the smallest key across all the SS table sources and keeps only the newest version of the key. So, when a sorted run occurs, the skip list is essentially traversing and writing the newest key to the SS table files, right? And then on compaction, when we're merging, we're always going to try to keep the latest version of that key. And if that version is a tombstone, then we obviously know to delete that key and not add it to the new SS table. Let's see. So compaction handles syncing, and when a compaction occurs, it's applied to the manifest file, and the manifest file, which we'll discuss later, is how we rebuild the LSM tree structure per column family on recovery. But yeah, essentially compaction it reduces read and write amplification, and it keeps levels tight to the actual data on disk. So we implement another aspect of Spooky, which is the DCA, dynamic capacity adaptation. So in TidesDB, levels can grow and shrink. So let's say you have 3 LSM levels on disk and L3 becomes full. A new level will be added, L4, and all levels will be recalculated on the on the actual L4 size, level 4 size, and then the LSM tree, each column family can the disk levels can shrink as well. So let's say L4 becomes empty, and now L3 should become the largest level. Capacities are readjusted on the fly. So self-tuning, it grows the tree, shrinks the tree, and it's all triggered automatically after essentially after each compaction cycle or when a level is removed. So when TidesDB has to recover, right, after a shutdown or something like this, what the system is going to do is read all column families, determine their SS table state, and read its manifest, right? The manifest tells us what SS tables were in what levels, all the information on the SS tables, such as the sequence number, like the highest sequence number in the SS table file. So the sequence number, we're gonna get back a global sequence number +1. So let's say you can see by the graph, right? We're gonna try the goal here is just to get back the last known sequence number +1 to be used for new transactions. So like when you do a read in TidesDB and you have a sequence number in your transaction, you're always going to see less than or equal to your sequence number on your read. Oh, and one more piece here is like when we're doing this, right, we're doing like the opening and validating like the log files and the SS table files and checking if like anything was corrupted and seeing, as mentioned, what has to be truncated or what has to be removed, that maybe there was an unsuccessful flush or unsuccessful compaction, that the valid SS tables live but the new one is corrupted, so that old one has to the new one has to be obviously removed. And so it deals with this all this stuff, right? It deals with crash recovery and validation, and yeah, the manifest is as well like the source of truth for each column family's LSM tree structure. So now for the engine to SQL. Right, putting TidesDB to work. We have TidesSQL or TidesSQL, however you want to pronounce it. It's a pluggable. It's a plugin really for MariaDB that allows you to use TidesDB. So the lock-free architecture, the concurrency, the transactions, and the speed with MariaDB. It really wraps all of TidesDB's functionality into one plugin, and you can use TidesDB really through engine equals TidesDB, right? Uh, yeah, let's get into how all this works, but yeah. So you essentially load the plugin in MariaDB. The TidesDB engine has its own database, has its own dedicated directory in which all the data lives. Each table in TidesSQL correlates to a TidesDB column family. So also primary keys and secondary indexes are their own column families. Uh, we do a lot of uh, unique things here with how we handle keys, right? So we have a like a mem comparable format. So we use like a sign bit big Indian type of hack here. So um, we essentially have like a pack binary self-describing header as well for the row values. Um, so yeah, we have like a names. We also have different prefixes determining like what you know what's a data row and what's for meta. Um, and yeah. So transactions in TidesSQL, we map to MariaDB's transaction model pretty much. But one thing to note is TidesDB is highly optimistic. So at the MariaDB level, it's good to, like, if you're going to have a lot of TPCC style workloads, it's good to use pessimistic locking, which you can set, which essentially enables like row locking, which TidesDB doesn't have at the library level, but you can enable at the plugin level, which uses like a sort of like a lock table. By default, the plugin uses repeatable read like InnoDB. Okay, we try to match InnoDB's transaction semantics. So DDL operations like alter, create index, truncate, optimize all use read committed isolation. So we have three tiers of alter table. Instant, which is like add column, drop column, renaming uh, columns, indexes, changing defaults, like the table options. So like each table can have like a different sync mode, different compression, bloom filter, block indexes, even a B tree, right? You can use a B tree or LSM, full like a B tree Klog or an LSM per table, which is pretty cool, and even like a per table index, which is pretty cool. Um, we have in place, which is like doesn't really block anything. So like adding, so like uh, so in place, concurrent reads and writes, nothing really gets blocked there. So it's like add index, drop index, creating like a new column family. Uh, and yeah, it really doesn't like it doesn't block any operations in place. Um, Copy actually does do like a full table rebuild. So this is like changing column family types. Um, yeah. So as mentioned, we have like per column per table tuning. So pretty unique feature set here. Like each table can have a bunch of different column family configurations. And then we have time to live, which can be like per row, per session, or at the table level. And we also have encryption as well. which is implemented in TidesSQL, which uses the generic MariaDB key management plugins. We have a few observability and operation options. Analyze table, which is obviously per we have analyze table, which it will give you like a per SS table counts, key so SS table key counts, mem table size, and information on that. Read amplification information for a like for the table, average key sizes and values, and even B plus tree statistics on the Klog if you have that configured. We have show engine TidesDB status, which will show you, the memory statistics, memory pressure statistic, cache metrics, and global sequence number statistics, queue statistics, conflict information, etc. So the plugin is completely like LSM aware. It's built in to the MariaDB optimizer. So yeah. TidesDB itself has a lot of statistics on like range queries, like how expensive might a range query be in this column family as opposed to the another, and this is all ties into MariaDB's optimizer. So TidesSQL is providing a lot of information, a lot of cardinality information, I guess you could say. We have optimized table, which does a synchronous flush and plus compaction. We have online backups, checkpoints, which uses the library methods, right? We pass that all into the SQL plugin. Now, the storage engine, when it comes to benchmarking, TidesDB, we like to benchmark using our bench tool with a baseline against RocksDB. In recent benchmarks, TidesDB does rather well against the industry standard RocksDB, and we continue always to obviously find different bottlenecks and profile and optimize the system, where we can. The bench tool is built to run obviously a lot of different patterns, a lot of different workloads, and that's how we're able to, identify and what to optimize, and just Another piece with the system is built on for modern environments, modern architect. Like, we with what we have today, with the modern systems we have today, there's a lot of performance left on the table, and we can clearly see that in the benchmarks, right? With the lock-free architecture and etc. And this indirectly translates to obviously TidesSQL. In sysbench benchmarks, we're looking rather good against InnoDB, which is a baseline. Right, now sysbench is rather simulated, so we're always working on more analysis, and this analysis we're doing is for on the TPCC and TPCH specifications, and we're trying to utilize HammerDB, and we are utilizing HammerDB to optimize these workloads for TidesSQL, and obviously finding the bottlenecks and continuing to improve the system. Obviously benchmark for your use case, but yeah. With that, I thank you for taking the time to watch this presentation.